recently we started developing a SMB solution for storage systems. And here we came to a kind of challenge because the world of storage systems is very diverse. Storage systems are different from a big racks, a lot of racks, to a virtual data centers, which are absolutely different. And the challenge was to fit our solution for each one of them. And that's what I'm going to talk about. Now, the title of my presentation may be a little bit incorrect because I'm not going to talk about all the protocols. I'm going to talk about file sharing. And mostly SMB because our company is dedicated to SMB. All our experience concerns SMB, but I very much hope that some of considerations will be also applicable to other file sharing. Now, integrating file sharing into storage is not easy, just because storage solutions are different. So here we have quite a number of challenges, because from one point of view, we would like to have our solution very generic. As being generic, it's better to have it as simple as possible. The smaller API is, the easier it is to integrate. From other point of view, as a generic solution, it should cover everything that SMB or file sharing protocol semantics provides. So it should have an extensive API. This one contradicts to the previous. And here we need to look for a kind of trade-off. Another trade-off will be between performance and flexibility. The common solution will provide less flexibility than a dedicated one. This is always true. Here we need to find a right compromise between those. The same about scalability. Scalability and flexibility contradict. This picture shows a top-level architectural view of how file sharing protocol couples with a storage solution. Here comes the network itself. Here is the wire. We need something to talk with the wire and to provide complete packages. The syntax engine is something that knows how the file sharing protocol looks like. So it knows to parse the incoming request, and it knows to pack an outgoing response. Here we have the engine, the component that handles the semantics of the file sharing protocol. And finally, we have the data itself. Data and metadata sits here. Now the question, does it resemble you something? Does this schema resembles you something that you are familiar with? It's, in my opinion, and I just found out it a couple of hours ago, this is very similar, very compliant to Microsoft protocol specification. Here we have relationship with other protocols. Here we have messages. Yeah, section 3, protocol details, and abstract data model, right? Now, what are our constraints when we connect file sharing protocol implementation to a data store? We need to be as fast as possible, because it's always concurrency is involved. We need to minimize latencies. What is a latency? Latency happens in context switch. By the way, we have a single thread solution for embedded systems. It doesn't have this problem. It's just one single thread, which is not good. Not good for storage. It's not efficient enough. So what can we do? We can minimize. So we do not use uncontrolled number of threads maybe one thread per CPU core or something like this. And anyway, there is some constraint that should be applied to multi-threading. And the final option is to decrease overhead of a context switch, to make context switch painless. Maybe user space solution can help us. We'll try to see it later. Where context switch happens? It happens between transport and syntax module. It happens between syntax and semantics. Of course, it happens inside because everything is concurrent. Low latency solution can be applied sometimes. The word sometimes I will explain a little bit later. But for instance, the networking can be user space. DPDK is a good example. But actually, to say the truth, DPDK does not fit well the needs of SMB protocol. I'm talking always about SMB protocol because we have experience with SMB protocol only. RDMA is another example. Now, when we go to lightweight threads, it may reduce but not eliminate the cost of context switches. Finally, we can try non-preemptive threading. And here comes another constraint that is not mentioned here on the slides, but the solution for storage that should be generic must be portable. It must be portable. You can say, well, almost all storage systems are based on Linux or Unix. That's true. But what happens that each one of them has layers above layers on top of the operating system, so that virtually it's yet another operating system. That's why the solution should be portable. And then such solution as non-preemptive threading or lightweight threads may be resolved during porting. Now, we are talking about the first big block, which is called transports. Please pay attention that I am using the word transports in plural. I will explain it a little bit later. And here we have the following possibilities. We have just sockets, and that's what we are using very wide. But these sockets apply very significant latencies. RDMA, SMBD over RDMA is a better transport from the latency point of view, but it is expensive. And user space solutions. Currently, we did not find user space solution that fits the needs of our protocol, but DPDK is a good potential candidate. When talking about user space solutions like DPDK, the gap happens between two sides of the picture. But because the client side talks TCP, and if the server side talks DPDK, we are losing. But if both sides can talk something message-oriented like DPDK, the performance may become really good. And this is similar to the RDMA case. You will never use TCP on one side and RDMA on another. The same must happen here as well. Syntax, and here please pay attention that I'm using syntax in singular. Syntax receives a request from transport module, parses it, validates, analyzes, and delegates to semantics. When response is transferred from semantics, the data and metadata is also analyzed and packed and transmitted through transport. This is a role of syntax which Seems very easy. Semantics. Semantics is our state. Transport from our point of view is stateless. The same about syntax. Syntax is stateless. Semantics is stateful. Here, the state of the protocol is the place where the state of the protocol sits. Here is an example of partial, very incomplete structure of a state object. Here, how the state database of SMB protocol looks like. Now, this sentence is not exactly correct. All those guys over here do belong to semantics, but they do not belong to file system semantics. That's the difference. We distinguish between file system semantics, and I will mention this a little bit later, and we distinguish between network semantics. This is more about network semantics and less about file system semantics. All the rest is file system. Now, the relationship is one-to-many, or maybe one-to-many. For instance, several transport may be plugged, and several file systems or several semantics may be plugged, while syntax remains more or less the same. When I'm talking about relationships, when I'm using the term one-to-many, it's not about multi-threading, it's not about concurrency, it's about the logic. A good example of semantics is anti-fence semantics, which matches very good the semantics of the SMB protocol itself. RPC semantics, or inter-process communication semantics, which is a kind of another semantics that always plugged in, and another semantics may be printing. Which components are cluster-wide and which are node-specific? For instance, syntax does not require clustering. Syntax may be per node. The same about transport, of course. But the semantics in cluster requires replication. That's why semantics is cluster-wide. Not all the entities that were mentioned earlier must be replicated. Here we mentioned those that we expect to be replicated. For instance, handles, the term handles, as far as I understand, does not apply to NFS, but is very widely used in SMB. Now, replication is a very important component from the performance point of view. The trade-off is between using something generic, more or less, and using dedicated replication. Dedicated replication is always better because it's a central component. It's the component that affects very much the performance and the scalability of the entire storage. It's very sensible matter, and we will talk where dedicated replication is possible, where common replication is possible, and where dedicated replication is the only possibility. So when we decide between common and dedication and dedicating solution, we have a couple of constraints. If the more components we are moving to a generic solution, the less will be the cost. If you have the same solution for any storage, it will cost less than developing in-house. The more generic the solution is, it is less effective. Dedicated solution will be always more effective. In the following slides, we will talk about three ways, three methods of putting a boundary between common and dedicated. Of course, when it concerns file sharing protocols and storage together. Here is the first option. Here, transport, syntax, and semantics are common. The data store, of course, is dedicated because it's always dedicated. It works good in a standalone server. We have some experience with this. We tried it on standalone servers. It's good enough. Clustering is also possible, but clustering must be generic or common, and it should happen over here. This is not easy, and currently we do not have much experience with this. Maybe it's a matter of future research. Now, the advantage of replication developed inside a generic semantic engine is still that it is dedicated. It's partially dedicated because we know exactly which entities we will replicate. So, for instance, we can use message-oriented network, message-oriented protocols, because we know that the size of the entity will not exceed reasonable limits. Another disadvantage here is that cross-protocol may be not easy to implement, yet still possible. When talking about cross-protocol, I also mean synchronization between networking and local changes. Method number 2. Here, those two guys, transport and syntax, are common one, while semantics and file system itself are dedicated. Performance will be better. The clustering happens here, so the clustering is outside this solution. Those two components are per node, and replication happens here. It's good for cluster storage. It's good for very scalable and fast clustering storage. Some states may be implemented here. Or maybe in other words, semantics is divided into two components. One smaller component will be common, another bigger one must be dedicated. When I am talking about those states that can remain in common, I mean such things like connections, shares, logged users, and a couple of others. Such things like persistent handles and handles at on must be in the dedicated component in this case, in this method. Now, about user space solution. User space solutions can be implemented over here, but not all of them. For instance, to implement user space solution in transport will be not easy in this case. Some user space solutions, like lightweight threads, can be reasonably applied here. And here we have the last option. The only common thing, the only common component that remains is syntax engine, while all the others, while all the others are dedicated. This is very suitable for top level, very efficient storage solutions. Here, in our experience, in this model, we can gain the best scalability and the best performance. Clustering, of course, remains outside the common component, and user space solutions can be applied everywhere, in transport as well as in over here, and in threads, in thread synchronization, everything. Over here, we have a table which puts together everything we were talking about. All three methods are here. In Visuality, we have experience with all three of them. Not with each of them, we have enough experience. Thank you very much.